Electricity is one of the most important gifts that science has given to mankind. It has also become a part of modern life, and it is impossible to imagine a world without it.
Used in home appliances such as room lighting, work fans, electric stoves, and air conditioners. All these provide comfort for people. In factories, large machines are powered by electricity. Food, clothing, paper, and many other basic things are products of
Control of power electronic converters in systems examines the theory behind controlling power electronic converters, including simple converter operation, modeling, and control. This report explores how power electronic converters and system components can be manipulated to achieve desired effects by controlling system variables. Advances in power electronics will open up new applications and improve the performance of existing applications. These advances depend on the effectiveness of the control, so it is imperative to apply appropriate control schemes to converters and systems to achieve the desired performance.
So here is the topic outline of our reports. We will discuss first the lesson outcomes of this report. At the end of this topic, the learner should be able to first, identify different application of power electronics. Second, to differentiate the six types of power converters and to determine their applications. Third, to familiarize with different power electronic devices and their symbol and characteristics. Fourth, to understand and be aware how utility power transmission and distribution system works. Fifth, to learn different methods of controlling power and to know their advantage and disadvantages.
So, before we proceed to the main topic of this report, we will discuss first the overview about power electronics. What is power electronics? Power electronics defined as the application of solid-state devices electronics for control and conversion of electric power. It deals with how to control and convert power or electrical energy into one form to another, and how to utilize power at high efficiency. What basically is power? Electric power is measured in watts and is calculated as a product of instantaneous current and instantaneous voltage. Energy, on the other hand, is the product of power over a period of time and is measured in watt hours.
So before we proceed to the conversion, utilization, and different methods of controlling power, we must first know how to generate, transmit, and utilize power. So with the help of this diagram, we may know how to generate, transmit, and distribute power. Power is basically generated at the power plants. Power plant generate AC electrical signals. These electrical signals is transmitted to the transmission line. But before the signal get transmitted, the signal is given to the step-up transformer. The function of the step-up transformer is to boost the power level of the coming signals. They boost the power at this level because the high signal has no losses during transmission as compared to the lower signal. That's why they boost the power level of the generated electrical signal within the power plant. Now, the boosted signal is given to the transmission line. Transmission lines transmit the signal to the long distance, and this signal is distributed to our home, to domestic or commercial applications. But before the distribution of power, the power is given to the step-down transformer. The role of the step-down transformer is just to reverse the role of the step-up transformer. The step-down transformer reduces the power level of the coming signal. Now the signal is distributed to sub-transmission customers, primary customers, and secondary customers. Power supply to our home is basically 220 volts and 60 Hz power supply.
Power electronics have already found an important place in modern technology and are now used in a great variety of high-power products, including heat controls, light controls, electric motor control, power supplies, vehicle propulsion systems, and high voltage direct current or HVDC system. Power electronics is basically a branch of electrical engineering which is extensively used in the processing and controlling of high voltages and currents in large industrial equipment, household equipment, and so on. Power electronics indeed have a lot of application, and it includes domestic, industrial, aerospace, and transportation.
Static converter is a power electronic converter that can convert electric power from one to another. The static power converters perform these functions of power conversion. The power semiconductor devices or power electronic converter controls falls generally into 6 categories. 1. Diode rectifier. Number 2. AC to DC converter or controlled rectifier. 3. DC to DC converter or the DC chopper. 4. AC to AC converter or the AC voltage regulator. 5. DC to AC converter or the inverter.
But before we discuss the different power electronic converters, we will first discuss the different electronic devices. To construct the different type of converters, they may require some power electronic devices, so here it includes. Power electronic converters mainly comprise of uncontrolled turn on and off, which is the power diode, controlled turn on, uncontrolled turn off, which is the thyristor, controlled turn on and off characteristic, such as power transistor, BJT, MOSFET, GTO, and IGBT. Continuous gate signal requirement, such as BJT, MOSFET, and IGBT. Pulse gate requirement, such as SCR and GTO. Bipolar voltage withstanding capability, such as SCR and GTO. Unipolar voltage withstanding capability, such as BJT, MOSFET, GTO, and IGBT. Bidirectional current capability, which is the triac. Unidirectional current capability, such as SCR, GTO, BJT, MOSFET, and IGBT. These are the most important types of power electronic devices which requires the construction of power converter. Here are the different power electronic devices with their symbols and characteristics. For diode, thyristor is ITH, GTO, MCT, MTO, ETO, IGCT, triac, LASCR, NPN-BJT, IGBT, N-channel MOSFET, and SIT.
Let us proceed to the main topic of this report, the 6th type of power converter controls. Number 1. Diode rectifier. A diode rectifier circuit converts AC voltage into a fixed DC voltage. The input voltage of rectifier could be either single-phase or three-phase. A rectifier is a special type of diode that converts alternating current into direct current. This is an important process as alternating current is able to reverse direction periodically while direct current consistently flows in a single direction, making it simple to control. There are multiple types of rectifier includes half-wave rectifiers, rectifiers that permit only one half of the AC signal to pass from input to output. The full-wave rectifiers, rectifiers that use the full signal, requiring the additional use of the transformer. Positive half-cycle rectification, those where a top diode with positive polarity conducts current while the bottom with a negative polarity blocks it. The negative half-cycle rectification, those where the top diode is black and the bottom one is open. The figure shows a full wave and half wave rectification. Full wave rectification rectifies the negative component of the input voltage to a positive voltage, then converts into DC utilizing diode bridge configuration. In contrast, half wave rectification removes just the negative voltage component using a single diode before converting to DC. Afterward, the waveform is smoothed by charging and discharging a capacitor, resulting in a clean DC signal. From this, it can be said that full wave rectification is more efficient method than half wave rectification, since the entire waveform is used. Also, a ripple voltage that appears after smoothing will vary depending on the capacitance of the capacitor and the load. Given the same capacitance and load, ripple voltage is smaller with full wave rectification than full half wave rectification. Of course, it goes without saying that the smaller the ripple voltage, the better the stability.
AC to DC converters. An AC to DC converter circuit can convert AC voltage into a DC voltage. The DC output voltage can be controlled by varying the firing angle of the thyristors. The AC input voltage could be a single phase or three phase. The process of conversion of AC current to DC current is known as rectification. The rectifier converts the AC supply into the DC supply at the end of connection. Similarly, transformers are normally used to adjust the AC source to reduce the voltage level to have a better operation range for DC supply. The AC to DC converters is used in almost all electronics and electrical devices. They are used as power supply circuits for household application like vacuum cleaners, washing machines, refrigerators, electric rice cookers. For daily life, usable products like computers, televisions, cell phone chargers, and etc. Indeed, AC to DC converters play a very important role. The figure 3 shows the full wave or bridge rectification. The bridge rectifier is a type of full wave rectifier that uses 4 or more diodes in a bridge circuit configuration to convert alternating current to a direct current. In a figure 4, it shows how sinusoidal waveform converts to DC after rectification. As you can see in the graphical representation, from alternating current it depicts sinusoidal waveform. It converts to a straight line that depicts the direct current, which are associated with constant voltages and currents. DC graphical representation is straight line because the frequency is zero and the value is unchanging over time.
DC to DC converter is an electrical system which converts direct current sources from one voltage level to another. In other words, a DC to DC converter takes input a DC and outputs different DC voltage. The output DC voltage can be higher or lower than the DC input voltage. As the name implies, DC to DC converter only works with direct current sources and not with alternating current sources. A DC chopper is basically a static power electronic device which converts DC voltage power to variable DC voltage. It is nothing but a high-speed switch which connects and disconnects the load from the source at a high rate to get variable or chopped voltage at the output. There are three types of DC to DC converters. Step-down or back converters. In a typical non-isolated step-down or back converter, the output voltage depends on the input voltage and the switching duty cycle of the power switch. In Figure 5, it shows a fundamental step-down of DC to DC converter topology. It is a class of switch mode power supply typically containing at least two semiconductors, a diode or a transistor. Although modern back converters frequently replace the diode with a second transistor used for synchronous rectification, and at least one energy storage element, a capacitor, inductor, or the two in combination. To reduce voltage ripple, filters made of capacitors, sometimes in combination with inductors, are normally added to such converters' output, load side filter, and input, supply side filter. Its name derives from the inductor that bucks, or opposite, the supply voltage. The output voltage is given by the equation output voltage is equal to the product of duty cycle and input voltage. Step up or boost converters. It is used to boost DC to DC converter voltage, and it uses the same number of passive components, but arranged to step up the input voltage so that output is higher than the input. As Figure 6 shows, a fundamental boost DC to DC converter topology is a class of switch mode power supply containing at least two semiconductors, a diode and a transistor, and at least one energy storage element, a capacitor, inductor, or two in combination. To reduce voltage ripple, filters made of capacitors, sometimes in combination with inductors, are normally added to such a converter's output, load side filter, and output, supply side filter. The output voltage is given by the equation output voltage is equal to input voltage over 1 minus the duty cycle. Number 3. Back boost converters. These converters allows the input DC voltage to be either stepped up or stepped down depending on the duty cycle. As Figure 7 shows, a typical back boost DC to DC converter topology. This is a switch mode power supply with a similar circuit topology to the boost converter and back converter. The output voltage is given by the equation output voltage is equal to the product of negative duty cycle and input voltage over 1 minus duty cycle. From the expression, we can notice that the output voltage is always reversed in polarity with respect to the input. Therefore, a back boost converter is also known as a voltage inverter. As Figure 8 shows, principal operation of a DC to DC converter. If we have two electrical systems operating at different voltage levels, one high level 120 volts and another low level 12 volts, a DC to DC converter can convert voltage between them from high to low or low to high. The conversion from one voltage level to another voltage level is done with power losses depending on the operating point of the DC to DC converter and type of the converter. The efficiency can be between 75 to 95% or more. Some key applications where DC to DC converters are employed extensively includes renewable energy integration and medical devices, vehicles, smart lighting, and other scale electronic appliances.
AC to AC converters. This type of converters, electronic converters, are used to convert the alternating current waveforms of a specific magnitude and specific frequency into alternating current waveforms with different magnitude and different frequency. As the signal remains AC, hence, this converter is termed as AC to AC converter. There are different types of AC to AC converters, and it includes cycloconverters, AC to AC converters with a DC link, matrix converters, and hybrid matrix converter. Cycloconverters. Cycloconverters are majorly called as frequency changers that convert the AC power with one input frequency to AC power. With a different output frequency, it can be used for changing the magnitude of the AC power also. Cycloconverters are preferred for avoiding DC links and to avoid many stages like AC to DC to AC, which is not economical and cause more losses. The cost of the DC link required will vary according to the ratings of the supply power being used. The figure shows the working principle of cycloconverter, wherein the input wave frequency changed by changing the firing angle applied to the thyristors. By switching the positive and negative limb thyristors, we can get a variable output frequency that can be step up or step down frequency compared to the input frequency. AC to AC converters with a DC link. AC to AC converters with a DC link generally consist of a rectifier, DC link, and inverter. In this process, the AC is converted into DC by using the rectifier. After being converted into DC, the DC link is used to store DC power and then again is converted into AC by using the inverter. AC to AC converters with a DC link is classified into two types. First, current source inverter converter. In this type of inverter, one or two series inductors are used between one or both lengths of the connection between the rectifier and inverter. The rectifier used here is a phase-controlled switching device like thyristor bridge. Second, voltage source inverter converter. In this type of converter, the DC link consists of a shunt capacitor and the rectifier consists of a diode bridge. The diode bridges are preferred for the low load as the AC line distortion and low power factor caused by the diode bridge are lesser than thyristor bridge. Matrix converters. Matrix converters are used for converting AC to AC directly without using any DC link, for increasing the reliability and efficiency of the system by reducing the cost and losses of the DC link storage element. Matrix converters consist of the bidirectional switches that particularly don't exist at the present but can realize by using the IGBTs, and these are capable of conducting current and blocking voltage of both polarities. Matrix converters are again classified into different types based on the number of components used. First, sparse matrix converters. The function of a sparse matrix converter is identical to the direct matrix converter, but here the number of switches required is less than the direct matrix converter, and thus the reliability of the systems can be improved by reducing the controlling complexity. Sparse matrix converters includes 18 diodes, 15 transistors, and 7 isolated reverse potentials are required for the sparse matrix converter. Second, very sparse matrix converter. The number of diodes is increased with the reduced number of transistors compared to the sparse matrix converter, and thus, due to more number of diodes, the conduction losses are high. The function of the very sparse matrix converters is similar to the sparse or direct matrix converter. Very sparse matrix converters includes 30 diodes, 12 transistors, and 10 isolated driver potentials are required for a very sparse matrix converter. And lastly, ultra sparse matrix converter. These are used for variable speed drivers of low dynamics as the input stage of this converter is unidirectional, and due to this, there is an admissible phase displacement between the input current fundamental and input voltage. Similarly, for an output voltage fundamental and output current is 30 degree, and hence, these are the majorly used for variable speed PSM drives of low dynamics. Ultra sparse matrix converters includes 12 diodes, 9 transistors, and 7 isolated driver potentials are required for ultra sparse matrix converters. Hybrid matrix converter. The matrix converters that convert AC to DC to AC are termed as hybrid matrix converters. And similar to the matrix converters, these hybrid converters also don't use any capacitor or inductor or DC link. These are again classified into two types based on the number of stages they take for conversion. If the voltage and current both are converted in a single stage, then that converters can be called as a hybrid direct matrix converters. If the voltage and currents are converted into two different stages, then that converter can be called as hybrid indirect matrix converters. As shown in the figure 13, AC to AC waveform conversion. The voltage and or current frequency are the parameters that might need to be increased or decreased. For voltage only, a transformer can be used, but for the frequency change and for both frequency and voltage change, use of electronic converters becomes necessary. Some of the main applications of AC voltage controller are the following: domestic and industrial heating, transformer tap changing, lighting control, speed control, or single space, single phase and three-phase AC drives, and starting of induction motors.
DC to AC inverters are designed to change direct current power supply to alternating current power supply. DC is relatively stable and positive voltage source, and AC oscillates around 0 volt based level, usually in square or sinusoidal fashion. DC to AC converters are one of the most important elements in power electronics. This is because there are a lot of real-life applications that are based on these conversions. The electrical circuits that transform direct current input into alternating current output are known as DC to AC converters or inverters. They are used in power electronic applications where the power input pure 12 volts, 24 volts, 48 volts DC voltage that requires power conversion for AC output with certain frequency. There are three major types of inverters. Number 1, sine wave, sometimes referred to as true or pure sine wave. A sine wave or pure or true sine wave inverters gives the waveform that you can get from hydroelectric power or from a generator. The major advantage of a sine wave inverter is that all the equipment which is sold at the market is designed for sine wave. This guarantees that equipment will work at its full specification. Second, modified sine wave. Actually, square wave a modified sine wave inverter actually has a waveform more like a square wave but with extra step or so. A lot of equipment will work well on modified sine wave inverters, including motors, household appliances, and other items. Some types of load can be problematic and do require a pure sine wave converter. Third, square wave. A square wave is very simple. With a DC supply switch between positive and negative, there are very few, but the cheapest inverter are square waves. A square wave inverter will run simple things like tools with universal motor without a problem, but not much else. A lot of equipment will work well on modified sine wave inverters including motors, household appliances, and other items. Some types of load can be problematic and do require sine wave converters. The DC to AC converters are used to charge the batteries in the vehicles, for driving low power AC motors in solar power system, and DC transmission lines for transmitting power to loads.
Static converter. Because the power devices can be operated as static switches or contactors, the supply to these switches could be either AC or DC, and the switches are called as AC static switches or DC static switches. The design of power electronics converter circuits requires design of the power and control circuits. The voltage and current harmonics that are generated by the power converters can be reduced or minimized with a proper choice of the control strategy. The static switches mainly find applications in relays, circuit breakers, UPS, flashers, and fuses. Along with these, they are also used in time delay circuits, transducers, and voltage detection circuits, and etc.
Let us proceed to another method of controlling power, switch method. In principle, the switching method is the simplest method of controlling power. As shown in figure 16, control consists of switch either to connect or disconnect the load from the supply. Control is limited to a simple off or on action. The AC power dissipates by the load is determined by the load current and voltage. This form of control is limited to situations where on or off control is all that is required. For example, controlling the temperature of stored water where the switch is actually a thermostat and cycles the load according to changes in temperature. The advantage of these methods are that it is simple and relatively inexpensive. The disadvantage are that it provides coarse control, relatively unreliable, and inaccurate that suffers from contact wear or fatigue.
Rheostat. Rheostat control uses a series connected rheostat or variable resistance, as depicted in figure number 17, to control load power. As resistance is introduced in series with the load voltage and hence AC power is reduced. The reduction in load voltage is caused by the voltage drop across the rheostat. AC power may be controlled from a very low value up to full power. However, for a wide range of control, the rheostat may be physically very large. It may in fact be larger than the load. To control the load power must be dissipated in the rheostat. This is a power loss and results in poor efficiency at low load setting. When the load power is reduced to 50%, the power dissipated in the rheostat is equal to the load power. This method of AC power control has the advantage that is very simple. The disadvantages are that it is very inefficient, bulky, very expensive when the running costs are taken into consideration, and has poor load regulation.
This method controls a load power in the same manner as rheostat control it, by varying the load voltage, but uses either a variac or tap inductor. This method are suited only to AC supplies and loads. The use of the variac or tap inductor overcomes the poor efficiency of the rheostat method. As shown in figure 18, a variac connected to a controlled load power. This method is very efficient. Efficiency in excess of 90% can be expected. Offers fine control and display quite good load voltage regulation. Owing to the high cost of mass of the variac, it is usually limited to low power applications. The sliding contact in the variac may also have wear problem. In figure 19, it shows a tap inductor connected to control the AC power in a load. The method is used for a speed control of ceiling fans and other low power applications. Control of high values of load power with this method would necessitate large, expensive inductors. The advantage of these methods are that it is simple and efficient, while it has the disadvantages that it is costly for medium to high power loads, as poor load regulation that and provides control only in discrete steps.
And lastly, the thyristor power control. Thyristor control has largely superseded all other methods of AC power control. It offers efficient and cost-effective control of power in most applications from very low to very high power levels. In Figure 20, it shows a simplified diagram for a thyristor power controller. Thyristors are a family of electronic devices designed specifically to provide power control functions. They are in effect controlled switches. Thyristors are turned on by a pulse of gate current, the gate being controlled lead on the device. Once turned on, these devices offer very little resistance and hence dissipate very little power, resulting in high efficiencies. Thyristor controllers achieve efficient AC power control by one or two methods. First method is phase control. The AC waveform is chopped up to achieve varying values of load voltage. The low voltage waveforms are no longer sinusoidal, but in many applications this is not a problem. The variable voltage is obtained by delaying the triggering of the thyristors, hence reducing the conduction time. An advantage of this method is that it may be applied to AC or DC load being supplied from an AC supply. It has the disadvantages that it produces radio frequency interference, or RFI, when the thyristor is triggered. The waveforms in Figure 21 represent typical load voltage waveforms supplied by a phase-controlled thyristor controller. The second method is zero voltage switching. This method of control device to overcome the RFI generated by phase control techniques. It operates in a similar manner to a thermostat in that load voltage is controlled by controlling relative on or off times. In this case, however, on and off times will be measured in cycles. For high power, the thyristor will be turned on for a large number of cycles, then it is off. The reverse applies for low power. To minimize RFI, the thyristor is switched as the supply voltage crosses 0 or is at 0 volts. Unlike thermostat control, this method may employ feedback from the load to provide accurate control. This method is suited only to resistive loads such as heating elements. It is unsuited to inductive loads. Typical waveforms are shown in Figure 22. And that's the end of our report.